Hi, this is Lisa McPherson here again with A Plus College Ready. This is video 2 for unit number 4, and the topic of conversation for this video will be spectroscopy. So the AP exam wants you to know quite a bit about a couple of different types of spectroscopy and then a few minor details about some others. So the two main types you need to know about are mass spectrometry, or spectroscopy, either works, and PES or photoelectron spectroscopy. Mass spectrometry separates atoms and molecules according to their masses, and so this helps us with determining how many isotopes an element has and what the average atomic mass is for an element. PES, on the other hand, uses high energy X rays or other high energy electromagnetic radiation to eject electrons off of atoms, and we measure the ionization energy, and then that data supports electron configuration. So we're going to look at both of these a little bit in greater detail and reading some of their graphs. The other types of spectroscopy that they want you to know something about are UV or ultraviolet and visible spectrum spectroscopy. You've probably done some work with this in the laboratory using either a spectrophotometer or a colorimeter. And these wavelengths of light are used instead of ejecting electrons like in PES, they just excite valence electrons. And those valence electrons, the electrons, as they become excited and move back down to lower energy levels, as we looked earlier, are going to produce light. And this is typically used to identify an element or a molecule or its concentration in solution, particularly colored solutions here. And you may have done a Beer's Law lab. If not, you might be doing it in this unit, where you determine the concentration of an unknown solution with a standard curve that you make from known concentrations of solutions using ultraviolet and visible light to do that. More on that a little bit later. Finally, infrared and microwave spectroscopy. These are lower energy forms of electromagnetic radiation, so they don't even excite electrons to higher energy levels. Infrared just vibrates bonds in molecules. So vibration and infrared is something you need to connect to each other, and this helps us determine the types of bonds or types of atoms or functional groups that occur within a molecule, like do we have single, double, or triple bonds in a particular molecule, or these carbon-hydrogen bonds or carbon-oxygen bonds, things like that, because different bonds vibrate at different energies. Microwaves and sometimes radio waves too, which are the lowest energy of electron in the electromagnetic spectrum, these just rotate molecules and rotate bonds, and it works really well with polar molecules. And this helps us to determine the molecular structure of a molecule. But the key word here is microwaves rotate molecules or rotate bonds compared to infrared vibrating and UV vis exciting valence electrons. So let's go back to mass spectrometry. In addition to knowing that it gives us information about isotopes, it's about mass. What else does it tell us? Well, here we have some mass spec data in the form of this graph, and notice that the x-axis is the mass to charge ratio across the bottom. Just kind of think mass in your mind will be fine. And on the y-axis is relative intensity. In this case, we're going from 0 to 100. Notice that doesn't mean that we have over 100%. This is just relative. This peak at 6 and the peak at 7, this one's just relatively much smaller than the one at 7. So there are a few things that we can tell about this particular atom or group of atoms, a sample of atoms from this mass spec data. So first it says how many isotopes are represented in the spectrum. Well, that's really easy. In this case, for this type of an atom, it's only 2. Sometimes the graphs for diatomic elements are a little more complicated because you'll see for each isotope of the individual atom, you'll have a peak for each one of those. Like chlorine, you'd have like a chlorine 35 and a chlorine 37, but you would also have Cl2 because it's diatomic. You would have double those. You'd have two more peaks at double 35 at 70 and another one at 74 for double 37. So they can be a little bit misleading. But here we have only two isotopes, one peak for each. It also asks which element does this spectrum represent. Well, then we want to look at the mass, and you can see that the mass of these two isotopes is going to be, the average is going to be somewhere between 6 and 7. And because the peak at 7 is so much larger, the average is going to be skewed much closer to 7. So it's going to be 6.8, 9, something really high like that. So you can go to your periodic table and look at your average atomic masses. You should be able to figure that out pretty easily. Then we also want to calculate the average atomic mass, but to do the calculations we need some harder numbers than we can read from this graph. So I'm going to give those to you here and say that the peak at 7 represents 7.42% of the sample of isotopes, and a peak at 7 represents 92.58%. So this again should be a review calculation for you. I'm going to give you a few minutes, pause the video here, and when we come back we will look at the calculation for that and the identity of our mystery element. Okay, so let's take a look. This is lithium because we have two peaks, and then our average is much closer to 7 than 6. And then you can see here down at the bottom of the page we've got our calculation where we take our percentage times the mass of the first isotope plus the percentage times the mass of the second isotope, divide that all by 100, and we get the average atomic mass here for lithium. So again, this is a review. You may want to work this on a worksheet, practice some more of these. A calculation you may need to be able to do on the AP exam. Now, the second type of spectroscopy or spectroscopic data that you may have to analyze is for PES. So PES can sometimes be more confusing. So let's take a look at this most simple graph. Notice on the x-axis it says energy is present here, and the scale is 0 to 10 from left to right. You need to be really careful with PES graphs because they do not always show energy increasing from left to right. Sometimes they are backwards and increase from right to left. So don't forget, one of the most important things when analyzing either graphical data or data in tables is read what the axes titles are, read the scales, read the titles and headings for columns and data tables, things like that before you start analyzing the data. So here we have this energy is increasing. For PES, this energy is actually ionization energy because we said PES uses X-rays and other high energy electromagnetic waves to eject electrons from an atom. Therefore, we're really using it to remove electrons from the atoms, so that's ionization energy. On the y-axis, we have relative number of electrons that are being removed. So how high the peak is tells us how many electrons were removed at that energy, and then where the peak is identifies where the electrons are, shall we say, as best as we can tell, in the atom, where they are in relation to the nucleus. Okay. Now remember that electrons are negative, nucleus positive, and the closer those two charges are to each other, the more attracted they are to each other. So electrons closer to the nucleus require more energy to remove. So these electrons that are out here at 6.26 compared to 0.52, these require more energy to remove. So those are closest to the nucleus, and therefore these are my 1s electrons. Now above this peak it has the number 2. You won't probably see that number there, but this is showing us there are 2 electrons here, so this represents our 1s2 electrons. This second peak over here though has a 1 above it. That's just to let you know, hey, look at the size of that peak. It's smaller than this other one. It's about half as high. And so because it requires these electrons require less energy to remove than the 1s. This is where our 2s electrons are, but there's only half as many of them. So we actually only have 3 electrons here, and I bet you can tell now that this element is lithium. So this is a very simple PES diagram. Let's take a look at one that's a little more complicated. Now, here we show, instead of a really long graph that we can't fit on the screen or the page, they've divided it up into 3 sections. So we have, again, along the x-axis, we have our ionization energy from 0 to 10. That's one scale. The second graph shows from 10 to 100. And the third scale from 100 to 500. So these are probably like in kilojoules or megajoules per mole of electrons removed. But in order to analyze this, we don't really need to worry about the units. Hallelujah. So what can we tell here? Well, again, peak height is relative number of electrons. And on these graphs, it's pretty simple because they've given you numbers that relate to the peak height. But don't expect to see those on the AP exam. So you have to look at the relative peak heights. Now, where are our valence electrons versus where are our inner core electrons, and which ones are the ones that are closest to the nucleus? Well, the valence electrons are going to be the ones that are easiest to remove, right? Those are the ones that come off first. They're farthest from the nucleus, so they're going to be the lowest energy. So it looks like these are our valence electrons right here. The ones with the highest energy, those are going to be, yes, the ones that are closest to the nucleus. So these are my 1s electrons. And as the energies decrease in value, so you got to watch your numbers, watch your scales, because again, they've assigned numbers or values to these energies, these ionization energies, but they may not be there on the AP exam on a graph you're having to analyze. You may have to just look at the scale and see, oh, these are higher energy than these. And by higher energy, remember, I don't mean higher energy electrons, because as electrons move further away from the nucleus, those electrons have higher energy. These energies are ionization energies. And as you move away from the nucleus, the ionization energies are lower because the attraction is less. So if these are my 1s electrons, where are my 2s electrons? Well, next lowest energy right there. And then followed by our 2p electrons. Okay, so those energy level 2 is there in my second graph, and then we jump out to the next energy level, and my 3s electrons are right there in this peak, followed by the 3p's. And notice that the p's in both cases, these peaks are about 3 times higher than the s's, because why? They have relatively 3 times more electrons in them that are being removed in that energy region. And then finally, what comes after 3p? Well, 4s. And because this 4s peak is one high, it's about half the height of the other s orbitals right here, right? Okay, this is a shorter peak, it has only 1 electron. So now we know this ends in 4s1. If you take a look at your periodic table, period 4, first square of the s block, what element is this? You got it, it's potassium. So this is really what you have to be able to do with PES data, is look at something with far fewer numbers on it perhaps than this. So be really careful about reading your scales and in which direction the ionization energies increase or decrease. And also remember, this is not the energy of the electron. Like in the Bohr model, this is kind of the opposite. This is the amount of energy required to remove it. This is the ionization energy. So be careful when analyzing PES data. So let's do a little bit of practice right here. Here's one little graph altogether. This graph is actually shown in your notes. And those little boxes, what I want you to do is do just like we did in the previous slides. I want you to pause the presentation right now, and when you well, not right now, but when you pause it, put in each one of these boxes. Is this 1s, and is it 1s1 or 1s2, 2s, 2p, etc. And let's see if we can label these peaks, and then we will come back to that here in just a minute. Okay, let's take a look at the answers here on this next slide. And you can see that the highest energy or ionization energy, notice they put that down here for us now in megajoules per mole, is 347, and that means these are the electrons that are closest to the nucleus. And then as the ionization energies decrease, we're moving farther from the nucleus. Again, don't let this fool you. Sometimes these PES diagrams have the nucleus out over here, they have high energies here, and they'll put 0 back here. And so the nucleus is wherever the highest ionization energies are, and moving away from the nucleus, going to lower ionization energies. So you can see here again, we're looking at potassium, but the graph looks a little different than the way it was displayed in the previous section. So be really, really careful about, don't try to analyze these too quickly and make simple mistakes. Okay, also UV Vis spectroscopy. Now, if you've run a Beer's Law lab already, you've probably looked at some of this, but this early part of it is probably what you glossed over and really focused on the end of the lab where you were trying to determine the concentration of your unknown solution, which is the ultimate goal. But there's some earlier work that we need to do so that we know what wavelength of light at which to analyze our known solutions to create our absorbance versus concentration graph. The absorbance versus concentration graph is what you're going to use to determine your unknown solution's concentration. You will measure its absorbance, and then you will track that absorbance over to this line, which is going to be your standard curve, standard linear curve, that you make from solutions of known concentration. And then from that absorbance, you would read a concentration. But how do we know what wavelength of light to perform this absorbance concentration experiment for to get this standard graph? Well, what you're going to do is first you're going to take some of your known concentrated solution and you're going to run an absorbance spectrum where you're running a lot of different wavelengths. Notice here we're going from less than 400 up to 700 nanometers in wavelength. And we're putting in one sample of a colored solution into the spectrophotometer and letting it check the absorbance, run the absorbance at all of these different wavelengths of light. And you will get this absorbance versus wavelength curve. Now, there's going to be a point on this curve where we have maximum absorbance, and we're going to see what that wavelength is right here. The wavelength at which we get maximum absorbance, if we run an absorbance versus concentration curve with standard known solutions, we're going to get a nice linear curve, and it's also going to give us the greatest change in absorbance for changing concentration that we can get. Notice if we choose not the maximum absorbance wavelength at some other point, our standard curve doesn't give us our greatest change of absorbance versus concentration. It's not as good a standard curve. So to get the best linear standard curve, we're going to want to use the wavelength at which we get maximum absorbance. Okay, so in this particular case, for this solution, it'd be somewhere, 515 to 520 nanometers. We want to run our absorbance concentration curve. Okay, so then what we do is we have made several solutions. We know what our solution is made of in this case, but we are making known concentrated solutions. So like maybe 1 molar and half, 0.5, 0.25, 0.1, etc. And then we're going to run check the absorbance at that maximum absorbance wavelength from our previous slide, and we're going to read the absorbances of those known concentrated solutions. And so we know the concentrations, and as noticed, as the concentration increases, what happens to the absorbance? It increases also. When we connect all those best fit line, we're going to get this standard curve. And a best standard curve is going to be very linear, and it's also going to end up at a zero concentration. We get zero absorbance. So we would really, really love for it to go through the origin right here, this vertex. Now, once you have the standard curve, now you can take your unknown solution. Don't know its concentration, but we can put it into the spectrophotometer or the colorimeter at the wavelength that we've chosen for maximum absorbance, and read the absorbance on our unknown solution. And then we will track that over to our standard curve and drop down a line to our concentration on the x-axis, and this gives us our concentration of our unknown. This is using Beer's law. Mathematically, Beer's law is represented on the AP equations and constants page with this equation, and it tells you on the constant sheet what A, B, C, and capital A mean, but capital A stands for absorbance. That is equal to little a, the molar absorptivity constant, which changes depending on what your solution is made out of. B is the path length, which for most of our devices is going to be 1 centimeter. It's the width of your cuvette. So these two, A and B, are constants typically, and then C stands for concentration. So you can see that A, absorbance, and concentration are directly proportional to each other, and A and B are our proportionality constants right there. So you may have to do a Beer's law calculation with this formula. They would have to give you A and B. They have to let you know what those are in the problem somewhere, and then they may also give you a graph of, like we have here, of absorbance versus concentration, and ask what, if they give you the absorbance, estimate the concentration. And they could also ask you about this maximum absorbance value right here. This is the wavelength at which you would perform this particular set of absorbance readings for all of your standards, to make this standard curve to determine what your concentration of solution is. So take a look at that. I think there's some videos that are posted that may run you through these calculations and reading the graph and relate it back to the labs also. Okay, so our next video is going to be on periodic trends. So we're going to stop video 2 here and pick up video 3 with periodic trends and periodicity next.